All right, good morning, Tigers. We're going to start with our very first video lesson today. So we're exploring lesson 1.1, investigating patterns, and we're going to be looking at different numerical and graphic representations of data. So since this is your first video lesson, just some good ideas. Make sure you have a printed copy of the notes for you to fill in along with the video. I will not fill in the entire page. Some of this will be left up to you to work. So always have your writing utensil, have a copy of your notes, be ready to pause the video to work out some problems on your own and check your work. If you just wait on me to give you the answers, that's not going to help you when it comes to quiz time. You need to practice and know what you're doing. So we'll just go ahead and jump in. So the first thing we're going to do is look at our learning targets. So in activity 1, in lesson 1, our learning targets are going to be that we can use units to understand and interpret problems. So that's our first goal, is we're going to be able to understand and interpret problems and use units of measurement to help us. So what we're going to do is we're going to circle all the verbs and underline all the nouns. I know that sounds like an English class, but this will help you visualize, okay, this is what my end goal is. We're also going to be able to choose and interpret appropriate scales for a graph. We can interpret parts of an expression. We can write an arithmetic sequence that models a situation. I'm not sure if models, well, we'll circle models, it's a verb. Okay, so we're going to understand and interpret problems. We're going to be able to choose an appropriate scale. We're going to be able to write a sequence and interpret different parts of an expression. All right, next thing we're going to look at. So we have some things that correlate with these notes. The guided video, which is what you're watching now, correlates with these notes. Assignment 1 and spiral review 1 also correlate with these notes. Okay, and so let's look at some of our vocabulary too. Some new words that you might be learning this unit would be sequence, common difference, consecutive terms, expression, and variable. Some of these you might already know what they mean, but in this lesson you should definitely learn what these are by the end of the lesson. Okay, so let's start with, okay, actually before we start, let me just point out one other thing, and I'm just thinking of stuff since this is the first video. What I want you to notice is that there is a crab in the left, on the left side of the box. Everything that has a crab on it will correlate with this lesson. So we did that. We've actually put clip art on here, and so all the matching clip art kind of goes together. So if you look, spiral assignment or spiral review 1 and assignment 1 should also have this little crab on it. And then if you notice, I've got my little Bitmoji that says woohoo. You should have your binder set up by now, and you'll have a tab that has me going woohoo, and that's the section that these notes go in. So we're trying to make this easy for you to organize as well. So we're going to leave it there, and let's start with task 1. So let's go ahead and get into the actual math. Okay, so Zing spent his summer vacation traveling cross-country with his family. Their first stop was Yellowstone National Park in Wyoming and Montana. Yellowstone is famous for its geysers, especially one commonly referred to as Old Faithful. A geyser is a spring that erupts intermittently, forcing a fountain of water and steam from a hole in the ground. Old Faithful can have particularly long and fairly predictable eruptions. As a matter of fact, park rangers have observed the geyser over many years and developed patterns they use to predict the timing of the next eruption. So fun fact, this summer I actually went to Yellowstone and got to see Old Faithful, and they actually, I have the actual formula they use. So this is kind of an approximation formula. I have the actual formula. I will show that to you another day. But this is the approximation of how long it takes for the geyser to erupt. So the park rangers have recorded all this information in a table. So number 1, describe any patterns you see in this table. So this is not a right or wrong answer. This is just, what do you notice in this table? So let's look at the left column first. So what does the left column measure? Well, it measures the length of the eruption. So column 1 measures how long the eruption lasts. Okay? So, like from the time that the water starts bubbling up till the time there's no more water and steam coming out of the hole. Let's look at the numbers in this. So what do you notice about the numbers? Are they increasing or decreasing? So I would say that each of these increases by 1. Okay? All right. So let's look at the second column. So column 2 is not measuring how long the eruption lasts. It says the approximate time until next eruption in minutes. So I like to call that your wait time. So this is how long you would have to wait for the next eruption. So we'll say wait time between eruptions. And is it increasing or decreasing? Well, let's see, we go from 46 to 58 to 70 to 82, so it is increasing. And what we noticed here was this was increasing by 1 each time. It didn't skip numbers. This one, let's see, does it increase by the same amount each time? So to get from 46 to 58, that's an addition of 12. From 58 to 70 is also an addition of 12, and it's also an addition of 12. So what we can safely assume right now is that the length of the eruption, or the wait time between eruptions, increases by 12. And I'm sure there's more patterns that you can notice. In years past, I've had kids tell me, hey, the wait time is always an even number. I'm like, that's great. That's a pattern you can notice. Let's see. We didn't have any negative numbers in here, which makes sense because are you going to have an eruption last negative minutes? That doesn't make sense. And we can't have a wait time that's negative because that would be going backwards in time, and I'm not a time traveler, so that doesn't work. So there's a lot of things you can notice in here. There's not very many wrong answers. Now, if you told me that these were the alphabet, I would count that wrong. But like, as serious answers, there's not very many wrong answers. You could tell me a lot of different things about this table. I think these are the two most important things that we need to notice, though. Okay. So number 2, why might it be important for park rangers to be able to predict the timing of Old Faithful's eruptions? So what I want you to do is I want you to pause the video and come up with 1 or 2 reasons why it might be a good idea for us to know when Old Faithful is going to erupt. And so I'm going to pause the video and I'm going to let you come up with some, and then I'll come up with a few as well. Okay, so I came up with 2 reasons. My first one was safety. You don't want anyone too close to the geyser when it erupts. I will say, like from me going there, they are pretty good about telling you how far you can go or how close you can get to it. It's kind of, you've got a walkway around it so people don't go past that walkway. But still, you've got people who don't listen, and so knowing that, oh, it's not going to erupt for another hour, let me go play on the geyser, even though that's a dumb idea, don't do it. You know, it's less of a safety hazard. And tourism. So this one is probably my biggest thing. There's so much to see in Yellowstone. You don't want to sit there and wait for an hour and a half waiting on Old Faithful when you could go see the geyser basin that's all different colors, or the wildlife. Like, I actually got to see a bear. I'm pretty cool. I'm pretty stoked about that. So, you know, there's so much to see in Yellowstone that you don't want to just sit there for an hour and a half waiting on Old Faithful to erupt when you can go, oh, I got an hour. Well, let me go run down here, see this geyser basin, and then come back and see this. So yeah, so there's a lot of different reasons. If you have something different, I'd love to hear from it. So like, you can either put it in the YouTube comments, you can comment on this on Google Classroom. So if you have a different reason, that would be kind of cool to know. Okay, so if an eruption lasts 8 minutes, how long must park visitors wait to see the next eruption? So explain your reasoning using the patterns you identified in the table. So again, I think I'm going to let you do 3 and 4 without me. I'm going to pause the video. So just some notes about 3. Just remember that our pattern we noticed was that for every minute, so let's write this down. For every minute the eruption lasts, so for every minute longer this is, the wait time increases by 12 minutes. Okay, so I'm going to leave that here. I want you to try 3 and 4. So go ahead, pause the video, and try this now. Okay, so you should have gotten that the eruption is going to last 130 minutes. So some things you could have done would be to continue the table until you got to 8 minutes. Also, we know that at 4 minutes we had to wait, for a 4-minute long eruption we had to wait 82 minutes. We could have also added 12 to that 4 times to get to the 130, or you could do 4 times 12 plus that 82 minutes. So let's look at, so there we go. I don't care how you got it as long as you got 130 minutes. There's a couple of different ways to approach it. And it did say explain your reasoning using these patterns. So I said for every minute the eruption lasts, the wait time increases by 12 minutes. So that's why I did 4 times 12 and then added it to the 82 at the end. So make sure you have a good explanation in there. This helps, but I also need to know, why did you do 4 times 12 plus 82, not 4 times 12 plus the 46 from the table? And we could say, well, we ended at 4 minutes with 80, that lasted 82 minutes. So I added 12 4 more times. So just something in words so I know exactly how you reach your conclusion. Okay, now number 4, there's going to be a couple of different things that people will have done this time. It does say graph the data from the table. So the table only shows us 1 through 4 and 46 through 82. So that's what I've graphed. If you went ahead and graphed more, that's okay. I'm not gonna, I get kind of picky on that because sometimes state tests and stuff get kind of picky on that. So I'm just being very careful with what I graph. If you continued this graph, that would be fine. One thing that is not okay, I'm gonna see a lot of people, well, no, actually I'm gonna leave that alone. I was going to say I'm going to see a lot of people graph a straight line through that. And to be honest, we don't know if, well, I think that would be okay. So let me just stop. This is asking us to graph the data and not the function or not the expression of it. So we're just going to graph these 4 points, and we're just going to graph points from here. If it asks us to graph the function, or if it asks us to graph our expression, we could conceivably draw a line through it. But here, just because it's asking us for that data from the table, we're just going to draw the points. Now, if you extended your table and you graphed those points, that would be fine. But we're just going to graph the points. We're not going to graph a line here. All right, so let's move on to the next page. So this is the back. Or if you're me, it's a separate page. So let's look at number 5. Reason quantitatively. Mizing and his family arrived at Old Faithful to find a sign indicating that they had just missed an eruption and that it would be approximately 2 hours before the next one. So how long was the eruption that they missed? So explain or show with math how you determined your answer. So a couple of things. We didn't measure our eruption or our wait time in hours. We measured it in minutes. So first thing you're going to need is how many minutes are 2 hours, and then find a creative way to figure out how long the eruption was. So I'm going to give you a few minutes. Go ahead, pause the video, and try this one yourself. All right, so there's a couple of different ways you can approach this. First off, let's remember 2 hours is a total of 120 minutes. You could have gone back to the table you wrote if you made the table. Let's see. Let me write this out here. So 120 minutes would be somewhere in between 7 and 8 minutes. So you would know it's a little over 7 minutes if you used your table. You could have also written an equation, which is what we're going to get to in the next set of lessons. After patterns, we get into solving equations and writing equations. So let me scooch this up so you can see the table. So I use this table to write an expression. Normally what we have is we have a 0 and another number up here. But the reason, why do you think there's no 0 here? Can you have an eruption that lasts 0 minutes? Well, no, because if it lasted 0 minutes, then it wasn't an eruption. So it wouldn't make sense. So that's why we don't have a 0 there. So normally we would, this number here in our expression would be whatever would be with 0. If we were to go by our pattern, which is increasing by 12, we could subtract 12 and get 34, which is where this number comes from. So we would have 12n plus 34 equals 120. And that 12 is because we're increasing by 12 minutes each time. Okay, let's look at the first equation I wrote though. So let's ignore the 0. We don't have the 0 and 34. But we do have a 1 and 46. So we could do 12n plus 46, but that's going to add an extra 12 minutes because if I plugged in 1 for n, you'd have 12 plus 46 instead of just 46 for 1 minute. So we had to subtract 1 minute from here. These basically are the same equation, just written a little differently. So you could go with either equation. And if you solve it out, you should get that n is 7.166667 or 1.7, or you could say 7.2. If you did a little math and finagling, you get that 7 minutes and 10 seconds. Whichever, either answer is correct. So it says explain or show with math how you determined your answer. So I should see, on yours, I should see more work than this. Remember, I'm not giving you everything because I don't want you to just sit and copy. I want you to think about it, struggle with the math a little bit. It's okay if you struggle. Struggling, there's something called productive struggle, and when you are actually struggling with the math and it's making you think and it's kind of making your brain hurt, it means you're actually learning it. So struggle is a good thing here. Okay, so let's move on to task 2, which is patterns as sequences. So if you remember, if you look back on your first page, sequences was your first vocab word. So let's figure out what a sequence is. And I think most of you have heard of a sequence, like a sequence of numbers, or if you type in, actually, like if you have a combination to get into your house, like a keypad combination, those numbers are in a sequence. It's more of a sequence than a combination, actually. So food for thought. Okay, task 2, patterns as sequences. So these patterns can be written as sequences. So if we look here, we have a little vocab blurb, and it says a sequence is a list of numbers, and each number is called a term of the sequence. So 2, 4, 6, 8 is a sequence. 2, 5, 10, 17 are sequences. What a lot of people are going to say is that it's a list of numbers with a pattern, and that's not true. It doesn't have to have a pattern to be a sequence. But some sequences do have patterns, and they're a little special. So what we're going to do is we're going to write the approximate times until the next, or the wait times as a sequence. Wait time is so much easier to say. So we're going to take that table from here, and we're going to write it as a sequence. So we start off with the number 46, and then 58, and then 70, and then 82. And then I know we found some more, but we're just going to, we don't have to list every single possible wait time. What if we have an hour-long eruption? That's gonna, I don't want to write all those numbers. So what we're going to do is we're going to put 3 ellipses, or an ellipsis, which is that dot, dot, dot. And we're going to put it here, and that just tells me that this sequence will continue. And if there's a pattern, we should be able to assume that it will follow that pattern. So we have 46, 58, 70, 82. Explain or show with math. Woo, that auto-corrected pretty roughly. Explain how you determined your answer. Okay, so this one's kind of weird because it's like, well, I just wrote the numbers down. So what we're going to say is I listed the given wait times in the order according to eruption length. I could have used the whole line, but I decided not to. Okay. So I listed the given wait times in the order according to eruption length. So yeah, that's it. So just a quick side note here. I'm going to put this on a little sticky. If I gave you this sequence, if I gave you this sequence, is this sequence the same as this sequence? And no, it's not, because this sequence, the sequence, in a sequence, order is important. Sorry, I can't get my words out. Order is super important in a sequence. So if we have this and this, these are two different sequences because the numbers are in a different order. So I just want that to be there. So number 7, how would you describe this sequence of numbers? So let's look from first term to the last term. We can say that they are increasing each term, increases. I'm going to say it increases by 12. So each term increases by 12. I think that's really all we have to say. You could say, again, like I said with the patterns, we can say that all the terms are even, all the terms are positive, all the terms are integers. There's a lot we can say there. Each term increases by 12 is perfectly fine. So there's a lot of things you can say to describe this sequence. I think this is the most important, but there's a lot of things you can say here. Okay, in table 5, or in the table, 5 and 8 are consecutive terms. Some sequences have a common difference between consecutive terms. The common difference between the terms is in the table, or between the the common difference between the terms in the table below is 3. So, all right, so let's talk about sequences and common differences in consecutive terms. So consecutive terms are numbers in order. So like 5 and 8 are consecutive terms because 8 comes directly after 5. 8 and 11 are consecutive terms because 11 comes after 8. 5 and 11 would not be consecutive terms. So consecutive terms are like side-by-side numbers. Okay. And then the common difference between the terms is 3. So let's think about what common and difference mean. We know difference means to subtract. Common kind of means the same. So if I were to subtract my consecutive terms, like 8 and 5, 8 minus 5 is 3. 11 minus 8 is 3. 14 minus 11 is 3. So I get the same number between terms. Does that make sense? Okay, so my common difference is 3 because when I subtract my consecutive terms, I get 3. So I'm going to let you do 8 and 9 on your own. This is going back to this sequence that we wrote in number 6. So I'm gonna let you do 8 and 9 on your own. You can check your answers in a minute, pause the video, and get started. Okay, so in 8, I just picked 58 and 70 as consecutive terms. If we come back to our sequence, 58 and 70 are side by side. You could have done 56, 58. You could have done 82 and 70. Perfectly fine. I just picked 58 and 70. That's why I put lots of different answers, because this is one of those that there's not just one right answer. However, in number 9, there is only one right answer. If I subtract 70 and 58, I should get 12 as my common difference. And that should make sense, right? Didn't we add 12 to get to the next eruption time? Or to the next wait time? We did that. We added 12 several times, so that would be our common difference. So that should make sense. Okay. So number 10, I'm going to kind of start you off on number 10. I'll let you figure out some of this on your own. Number 10, each term in the sequence above can be written using the first term and repeated addition of the common difference. For example, the first term in this sequence is 5. The second term is 5 plus 3, which equals 8. The third term can be expressed as 5 plus 3 plus 3, or 5 plus 2 times 3, which would give us 11. So let's, we're going to do the same thing with the wait times for the eruption. So let's think about this. So for eruption 1, so if we have a 1 minute eruption, we have a 46-minute wait time. For a 2-minute eruption, we have that 46-minute wait time plus another 12 minutes. For our third eruption, we have that 46-minute wait time plus 12 minutes plus another 12 minutes, which we can write this as 46 plus 2, plus 12 times 2. Let's do it that way. That makes more sense. Okay. I'll do 4, and then I'm going to let you do 5 on your own. So for 4, we have the 46-minute wait time plus 12 minutes if it was 2 minutes long, plus another 12 for 3 minutes long, plus another 12 for 4 minutes long. What do you notice about the number or the length of the time, the length of the wait time, and how many times you write 12? That's going to come in handy in just a minute. All right, so I'm going to let you do 5. Pause the video and come up with your answer for 5. Okay, so this is one of those that I think you've got the pattern. I'm not going to write it down. You can check the key later to double check your answer. All right, so let's look at B. We're going to let N represent the number of minutes an eruption lasts. So we're going to write an expression using N to determine the waiting time until the next eruption. Okay, so what we're basically going to do is we're going to replace, instead of doing 12 times 3 and 12 times 4 and 12 times 5, we're going to replace this with N. But I want you to notice something. So I asked you earlier, what do you notice about 4 and the number you multiply by 12? Well, we're not multiplying by 4, we're multiplying by 3. So if N is how long the eruption lasts, I'm not plugging 4 in here, I'm plugging 3 in. So what am I doing to 4 to get to 3? Well, I'm just subtracting 1. So we're taking this N minus 1 and multiplying it by 12. But we have to consider that we also have that 46-minute wait time for a 1-minute long eruption. So we're going to add that 46 in. And this should match what we've done here. So let's double check this. C says check the accuracy of your expression. So when we say check the accuracy, what we mean is we want to take something we've already done. So we know how long a 2-minute eruption lasts. We should see a 46 plus 12, which is 58. So if I plug 2 in for here, I should get 58. If I don't get 58, that means I've done something wrong. Now, if you wrote something different here, and you did it wrong, and you got your answer wrong, does that mean you stop, like you don't know what you're doing? No, that means we have to tweak it. You can always, that's why I love math. If you do something wrong, you can go back and correct it. You can always fix it. There's ways to check yourself to know whether or not you did something right or wrong. So let's try this. So we're going to do 12 times 2 minus 1 plus 46. Okay? Now follow your order of operations. 2 minus 1 is in parentheses, so that would be 12 times 1 plus 46. 12 times 1 is 12, plus 46 is 58. And if we go back and check our table from earlier, a 2-minute long eruption should have a wait time of 58 minutes. Okay, so our expression is accurate. Now, had you done this and gotten the number other than 58, that would tell you, okay, I need to go back and fix my expression. And that happens all the time. That's why we build in these, check the accuracy, double check your expression. We build that in so that you have confidence in that your answer is right. I would rather you check it and see that you're wrong and go back and fix it than just give me something and it be wrong. So this gives you an opportunity to correct yourself. Okay, D says, use your expression to determine the number of minutes a visitor to the park must wait to see another eruption of Old Faithful after a 12-minute eruption. So what you're going to do, and I'm not going to do it for you, I'm just going to set you up. You're going to take your expression, you're going to plug in the number 12 for n, and you're going to simplify. The answer to this will be on the key. I'm going to leave it here. Thank you for your attention. I know this was a rather long video. I'm hoping that the future videos won't be as long, but I did want to kind of walk you through the very first lesson. So I hope you guys have a great day, and I will talk to you soon.